when we left things in the last class, having been interrupted by the missing Apple Pencil, which it turned out was hiding in plain sight in my kitchen, we were three-quarters of the way through the one-way independent groups ANOVA. So this presentation has been recorded to cover that material. So I think we'd gotten to the step where we were about to prepare the ANOVA summary table. The next slide shows the ANOVA summary table that we would prepare. The ANOVA summary table basically allows the reader to take in the main details of the analysis at a glance, and it provides us with the sums of squares, the degrees of freedom, the mean squares, the value of f, and the probability value associated with that f value for the analysis. It sometimes provides us with a clear hint that the investigators have misorganized their data. So it should relate very clearly to the number of levels of the independent variable in the experiment, the number of subjects that you have included in the experiment, etc. And so if there's a discrepancy between the ANOVA summary table and your understanding of the details of the experiment, then that's something to be concerned about. Essentially, it allows the reader to take in the main details of the analysis at a glance. A sentence should accompany the summary table that states, one-way independent groups ANOVA showed a statistically significant difference in response to the drug dose, and then in parentheses describes the F statistic calculation details, including the degrees of freedom, the value of F, and the probability level. Now, you will recall that I have said that the analysis needs to interpret the results in terms of the original question posed, and this only goes part of the way because it doesn't tell us which, if any, of the drug doses was effective. And these questions are answered by the follow-on tests that we will do once we have calculated a statistically significant F statistic. So the question remains, where is the effect? Which means differ from one another? We answer this question using post hoc tests on differences between the means. And if we look at the graph in terms of our response, it seems that clearly there's a difference between the placebo and the third dose, but we don't know if the third dose is more effective than the second dose, and so on, third dose being more effective than the first dose, etc. So in interpreting the results in terms of the original research question posed, we need to go a little bit further with follow-on tests. And so post hoc tests on differences between the means will answer the question, where does the statistically significant effect lie in these data? So the last steps in our one-way independent groups analysis of variance involve completing post hoc tests on the differences between the means and conducting an effect size analysis. So a significant F ratio only tells us that there's a significant difference somewhere in the data. Post hoc tests on differences between means are applied to determine where in fact do these differences lie. And these are all omnibus tests, so the nominal alpha remains the same no matter how many contrasts are made. So you will recall that we've talked about how you need to adjust the nominal alpha level from 0.05 to something else if you're conducting more than one test, and we've discuss this as it's called, the so-called Bonferroni correction. An omnibus test protects the alpha level at the nominal level, so for instance in this case at 0.05, no matter how many pairwise comparisons you're making. So this is an important thing to remember about Tukey's. Several possible post hoc tests on differences between means are available. We're going to use Tukey's honestly significant difference, or HSD. So let's continue with the present example. There are 4 steps to completing the Tukey's honestly significant difference test. First of all, you cast all the pairs of means into a table. Second, determine the absolute value of the difference between each comparison. Third, determine the critical value of Tukey's HSD using a table. Fourth, determine which pairs of means are the same and which are different. So let's first of all start by casting all the pairs of means into a table. Here we have all the pairs of means in our experiment that are cast into a table. So comparison 1 and 2, the mean for group 1 was 28.86, the mean for group 2 was 25.04. Comparing 1 and 3, we're comparing 28.86 with 22.5, and the comparison between 1 and 4 was 28.86, compared with a mean of 22.3, and so on, comparing each of the different pairs of means. Next, we determine the absolute value of the difference between each comparison, and this is shown in the next table. So the difference between means 1 and 2 is 3.82, differences between 1 and 3 is 6.36, 1 and 4 is 6.56, and so on, all the way down to 3 and 4, which are not that different, being different only on, which are not that different, showing a difference only of 0.2. The next step, we determine the critical value of Tukey's honestly significant difference using the formula as depicted on the table, and we need to know several different pieces of information. First of all, we need to know the significance level for this calculation. Once again, it will be alpha equals 0.05. We need to know K, the number of groups. In this case, we have 4 groups, 4 levels of the independent variable. We need to know the degrees of freedom within, the degrees of freedom associated with the within groups ANOVA term. In this case, it's 16, and the mean squared within term, which in this case is 7.27. Finally, the number of scores on which each mean is based. So we have a table, Tukey's Q scores for Tukey's method. We're going to be using the panel on the left because that's the alpha 0.05, and we use the table to determine the value of Q for our values of K and degrees of freedom that apply in this experiment. So with this, we know that the value of K is 4, the degrees of freedom are 16, and so the value of Q for our calculation will be 4.05. Highlighted the relevant values for the alpha at 0.01 just for fun. If we were using the 0.01 alpha level, the value of Q would be 5.19. But since we're not, we're using alpha equals 0.05, we will use 4.05 in our calculation. The next step shows the critical value of the honestly significant difference following the formula that we've previously defined. So honestly significant difference at 0.05 is equal to 4.88. If we were using the alpha level of 0.01, the honestly significant difference would be 6.27. So since we're using 0.05, we determine which pairs are the same and which are different. These are highlighted in the table. Group 1 is different from Group 3, and Group 1 is different from Group 4. All the other mean differences are not statistically significantly different. It can be helpful to portray this graphically. So let's group these different means in terms of Tukey's honestly significant difference. So it's telling us, first of all, that the first dose is not different from the placebo, and it's also telling us that 1, 2, and 3 are not different from one another. If we combine this, it looks like as portrayed in this graph, and what this is telling us is that the minimally effective dose, the minimally effective treatment in this experiment is dose number 2 to achieve a statistically significant effect. Last step in the one-way independent groups analysis of variance is to calculate an effect size. Even though we've computed a statistically significant value of F, and the analysis is showing us that there is a statistically significant effect, a statistically significant effect is not always substantively significant. So we conduct an effect size analysis to determine if this is something that's really worth paying attention to, or maybe not. Maybe it's not so important substantively. Effect size is calculated as follows. Eta squared is equal to the sum of squares between term divided by the sum of squares total term. We've completed the calculation here, and our effect size is 0.546. Any value of eta squared that's greater than 0.15 is determined to be a large effect. Between 0.06 and 0.15 is determined to be a medium effect, and between 0.1 and 0.6 is determined to be a small effect. So the effect of the independent variable in this experiment is a large effect, and we interpret this as saying that 55% of the change in the dependent variable, that's to say the blood concentration of some dependent measure, can be accounted for by the independent variable. So this is quite a large effect in terms of experimentation. This would be something that you would be interested in pursuing further and would be commercially meaningful to a client that you had. I've prepared some companion videos describing how you would complete this one-way independent groups analysis of variance using Excel, a software package called Stats Homework, and another stats package called GraphPad Prism, and these are all available on companion videos. Next in this series, we'll consider the two-way independent groups analysis of variance. Thank you for your attention, and have a good day.